All right, let's finish up with our final triangle congruency shortcuts in lesson 5.4, and this starts on page 303. So we have two more congruency shortcuts. Let me just tell you what these mean. ASA, notice just three parts, two angles and a side, but the fact that the side is between them is important. It's two angles and the included side. So the side falls between the two angles in the triangle. That looks like this. So you have a triangle and you have an angle, and then the side that falls in between the two angles or connects them. That is what we call the included side. The other shortcut is two angles followed by the side. So in other words, in this case, you've got two angles and not the included side. We call that a non-included side. Okay, so you have a triangle, and by the way, there would be two triangles, but you've got an angle and another angle, and then either of the two sides that does not fall between it. This is what we call a non-included side. Both of these are triangle congruency shortcuts that we can add to side, 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 and side, angle, side from lesson 5.2. So let's use those. Let's look for and use those shortcuts. So we're going to prove that triangle ACB is congruent to triangle ECD. So the first thing they tell us is that angle BAC, which is this one, is congruent to angle DEC. They say it was given. They go on to tell us that segment BD, this segment bisects, so it's doing the cutting, it bisects AE. This is the one that gets cut into two equal parts. So we knew it bisected AE because that was given to us. So now I know that this part has to be congruent to that part, definition of a segment bisector. So now I've got a pair of angles and a pair of sides, but I'm out of given information. Well, the only thing else I know for sure looking at this picture is that those are vertical angles. So ACB is congruent to ECD, and we know that because the vertical angles theorem says that vertical angles are congruent. I prefer you to just say that. And then there you have it. We have a pair of angles, the side between them, and another pair of angles in both triangles that are congruent. So they're congruent by angle, included side angle. All right, so let's do this one. We've been given two pair of parallel sides. The first pair has not been written in my proof. WX runs parallel to YZ. I'm gonna mark those. WX is parallel to YZ, and then they also tell us that WZ runs parallel to YX. I'm going to mark those differently. How do we know that? It was given. All right, now be careful because we're going to have vertices, all, letters all over the place, but this is really important. They tell us that angle WXZ, which is this one, is congruent to YZX. And the reason I know that is because those angles are in between the top and bottom of this parallelogram on opposite sides of the transversal. Notice that this angle is formed by the top side in the transversal. This angle is formed by the bottom side and the transversal. But any way you slice it, we have parallel lines. So we know that alternate interior angles are congruent to each other. That's what kind of angles those were. Now they want us to use the alternate interior angle theorem again. And the theorem basically says that the parallel lines come first, then you have the congruent alternate interior angles. Well, the other parallel lines that we haven't used yet are these two sides, and inside of those sides, that side forms this angle with the transversal, and this side forms this angle with that same transversal. Those are inside the parallel lines on opposite sides of the transversal. So what are the names of those angles? This angle is WZX. Angle WZX is congruent to this angle is angle YXZ. Angle YXZ. Alternate interior angles theorem. So now in these two triangles that we're trying to prove congruent, we have a pair of angles marked and another pair of angles marked. We need something else, and once again it's coming from the reflexive property. So what do they share? They share side XZ. XZ is going to be congruent to itself by the reflexive property, and now I have three things marked, and in each triangle I've got two angles and the side that falls in between those two marked angles. So it's an angle, their included side, and another angle is the reason we can say the triangles are congruent. So how can we use that to come up with some missing measures? So there's a window company that makes these hexagonal windows, but notice the hexagonal window is really formed by 6 smaller triangles. They tell us that PQ is running parallel to TS down here, and R is the midpoint of segment PT. So we know it's going to split that up into 2 equal pieces, and they tell us that segment ST is 12 inches long. That's what we know. So is triangle PRQ up here going to be congruent to this one on the bottom? Well, we know we've got parallel sides, so we're going to be able to say that angle RPQ, if you come down that transversal, it's an alternate interior angle with this one down here. They're both inside the parallel lines on opposite sides of that transversal. That's angle STR. Angle STR. Alternate interior angles theorem. The parallel lines guarantee the congruent angles. Because R was the midpoint of segment PT, I already marked it, we know that TR has to be congruent to PR up there by the midpoint theorem. And then angle TRS is this angle, is going to be congruent to this one, QRP. Those are vertical angles, and vertical angles are congruent. And so therefore, those two triangles are congruent by angle. By the way, I should have marked those two angles differently, but angle included side angle. Angle included side angle. Just give me a second, something has blown away. I need to grab it. All right, next question. Okay, so let's look at a couple of proofs and then we'll be finished here. So we've been given 2 statements in this diagram, and that is that, oh wait, excuse me, the wind blew my page over. I'm sorry, we have a little more to do. So let's find the area of the whole hexagonal window here. Well, an area formula for a triangle, the area of a triangle is 1/2 the base of the triangle times the height of the triangle. And they tell us that the height of TRS is about 10.39 inches. So that's this distance right here, 10.39. The base is 12. So we're going to do 1/2 the base times the height, half of 12 times the 10.39, and we get this. That number represents the area of one of those triangles, but the window is made up of 6 of them. So if you take the area and multiply times 6, that's going to give you the total area of glass that's needed to make the window. All right, I think I'm actually going to skip over this and we'll try to pick this up in class together just to speed things along. All right, let's just practice using angle, and then the non-included side, So notice here, they tell us that A and D are congruent, B and E are congruent, and then we have a pair of sides, but that side is not falling between the 2 angles. So those angles are congruent by angle, side. So let's do our own proof down here. L is congruent to Q, M is congruent to R, and we've got a pair of sides marked congruent. So they took all of that given information and said, oh, excuse me, so what they're doing is they're proving angle side by using angle side angle to prove it. So in this particular case, you know, if you've got two pair of congruent angles, then the third angle in each triangle has to be congruent. And then once you say that, you can see that you have two angles in an included side, two angles in an included side. Let's go over here to the next page where we'll do the proofs ourselves. All right, so we've been told that RQ is congruent to ST and that they're parallel to one another. Both of these given statements have been written. So we know that they're parallel to each other. As a result of that, they're saying that angle RQS, which is this one, has to be congruent to TSQ, which is this one. We'll notice that both of those angles are on opposite sides of that transversal inside those parallel lines. So how do we know that? We know that anytime you have parallel lines, the alternate interior angles are going to be congruent. This book calls that the alternate interior angle theorem. Okay, we also were told that the sides were congruent. And notice that the reason here is one of our congruency tests. So this is where I'm going to say that I have two congruent triangles in just a moment, but we need one more piece of information, and it looks like we want to use the fact that we know that vertical angles are going to be congruent to each other, and these are the vertical angles in the picture here. Angle RUQ, angle RUQ is congruent to angle TUS. Vertical angles are congruent, and now you can see that we have a pair of angles, but not the side that falls between them. In both cases, angles, not the side between them. So that's angle, side, but we do have the information now to say that triangle RUQ is congruent to triangle TUS. All right, let's do one more. All right, so in this particular case, I hope you can see, this will be a little tricky. We have these overlapping triangles. So we have triangle, if I could erase what I have covered up, we have triangle ADC, and then if I could erase those two parts, we have triangle BEC. And those are the two triangles that we're trying to prove congruent to one another. All right, they tell us that DAC, which is this angle, is congruent to BEC, this one. Angle DAC is congruent to angle BEC. We knew that because it was given. And they also tell us that DC is congruent to BC. So this piece is congruent to that one. And I know that because it's given. I want to prove that I have a pair of congruent triangles. So we're out of given information. Is there anything else that I know about these triangles? Well, usually what we've seen is a side that they share, but that's not the case. In this, let me draw these two triangles smaller. I don't know, sometimes it helps to separate them. So we have ADC and we have BEC. And we said that this angle was congruent to that one, and we said that side BC was congruent to side DC. So those are the parts that we have marked congruent. But though I want you to see that they do share something. They overlap one another down here at angle C. That's the same angle in both triangles, so C is going to be congruent to itself by the reflexive property. Angle C is congruent to angle C, reflexive. And now let's check the parts. ACD. So AC is the side that runs between the two angles that I have marked, and CD is the side that is ticked. Is that the case over here? ECB. Well, EC is the side that runs between the two angles, and CB is the side that's marked. So it looks like all the parts match up, and notice it's two angles and the side not between them. So that's angle, angle, and then the side.